So in the last lecture on equivalent statements, we saw how to show the two statements are equivalent by comparing their truth tables. And that's fine. It's a perfectly good method to use, but sometimes, especially when the statements get big, it can be awkward. It can be time consuming. Right? So one way around this is we can use statements that we already know to be equivalent to almost, in a sense, simplify an expression until we simplify it until it becomes equivalent to the thing we're trying to show it's equivalent to. And this is a common theme that you're going to see throughout the rest of this class and through mathematics in general. We don't always go back to the most basic method. We don't always go back to the definition when we want to prove something. If you've taken a calculus class, you've seen a lot of this. We start off by coming up with a definition of a derivative, and it's a good definition, but it's not very user-friendly. In a lot of situations, it can be really very difficult, almost impossible to use. So what we do is we derive formulas. We derive the product rule and the quotient rule and the chain rule. And these other rules are easier to use, and then we use them instead. Well, we can do something similar here. All right, so take a look at this equivalence. I want to show that these two statements are equivalent to each other. Now I'm looking at that, and I'm seeing De Morgan's laws in there, right? I'm seeing a negation, and we have a single operator here in the middle, but it doesn't exactly match. De Morgan's law doesn't say not P and not Q. It says just P and Q. Okay, so here's what I'm going to do to show this. I'm going to say, look, what De Morgan's law says is the negation of an expression or another expression is equivalent to the negation of the first thing and the negation of the second thing, whatever those things are. Right? So what De Morgan's law is telling me is that not P and not Q is equivalent to not the first thing, that's not P, or not the second thing, that's not Q. Okay. Now you remember from the list we saw, the double negation property says that not P is just P, and not Q is just Q, and that's what I wanted. Right? That's the second side here. So I have shown that the left side is equivalent to the right side very quickly. I mean, I can knock out a truth table pretty quickly, but not as fast as that. Right? So you see how we can get some efficiencies here using these known logical equivalences. So here we have a more complicated statement that I would really rather not try to do using a truth table. So let's see what I could do using our known equivalence here. First, let me just write out the left-hand side. And the first thing that jumps out to me is this bit here, all the way deep inside the parentheses. That I can apply De Morgan's law to. So this is equivalent to P and not P and not Q, or P and Q. Now I've got that double negative here on this bit. So this is equivalent to P and not Q, or P and Q. All right, now notice in this first parentheses here, right, all I have in there are ands. So what I can do here is I can apply the associative property and make this P and not Q, or P and Q. And P and P, the idempotent law, one of them says that this is equivalent to P. So this is P and not Q, or P and Q. Now, here it gets a little interesting. Notice how both of these pieces start with P and Q. All right, so I'm going to use the distributive property here. I'm going to bring out that P and Q, much the way we factor, right, in an algebra setting. What's left is not Q or Q, right? And if we look at one of the negation laws, Q, not Q or Q, is a tautology. So this is equivalent to P and T. And P and T, according to the identity law, is just P. And that's what we wanted to show. Right? That's it. There's the equivalence that we were looking for. Okay, so now we've got a good start, right? We've looked at several different logical operators, and we've seen some of the ways that they kind of interact with each other when the statements start to get bigger. In the next sequence of lectures, we're going to add two more operators. We're going to add what's called a conditional and a biconditional. The conditional in particular is really super important in mathematics. It's represented using an arrow, but the English version is if, then. And that kind of if-then statement is really at the heart of an awful lot of mathematical theorems.